Today we discuss differential equations of the form a, the second derivative of y with respect to x, plus b, the derivative of y with respect to x, plus c, y of x equals 0, where a, b, and c are constants. This is a form of differential equations that we can often find in a calculus course. These are second-order linear homogeneous differential equations with constant coefficients. Because the equations are second order, the general solution will consist of two independent parts, each with a constant. The solution will make use of the property of e to the x being its own derivative. Extending that to the derivative of e to the ax equals a e to the x will also be important. We will solve a simple second-order differential equation. 2, second derivative of y with respect to x, plus 5, the derivative of y with respect to x, plus 3, y of x equals 0. The technique is to consider the quadratic equation with the same coefficients as the differential equation and factor. If factoring doesn't work, the quadratic formula is acceptable. We don't have to factor, but factoring is what we normally start with. So we'll write a quadratic equation that has the same constants as our differential equation. 2x squared plus 5x plus 3 equals 0. And factor 2x plus 3 times x plus 1 equals 0. Next, we solve the quadratic equation and we come up with x equals -3/2 and x equals -1. And we will use these as multipliers of x as part of the exponential exponent on e to the x. So we're going to end up with e to -3/2 x and e to the negative x. You don't have to show explicitly a 1. I just did that to make it obvious what's going on. The general solution of the differential equation, and this is the one we started with, is y equals a constant times e to the -3x over 2 plus another constant times e to the negative x. So we have two constants that are distinct. Case 2. When the quadratic produces only one solution with multiplicity 2, there is a need for a second independent solution. So here we have, as another example, we're going to want to find the general solution for the second derivative with respect to x of y of x plus 6 times the derivative of y of x with respect to x plus 9 times y of x equals 0. Now, the quadratic equation x squared plus 6x plus 9 equals 0 factors as x plus 3 squared equals 0, which gives us x equal -3 multiplicity 2. But remember, I need two independent solutions to the second order differential equation. So the two independent solutions of this differential equation are y equals c1 e to the -3x, just like we had done in the earlier example, plus c2x e to the -3x. This X is now uh, giving us something that's independent and actually will work. Notice that the second term in the general solution has an X multiplier. This gives two independent solutions of the differential equation, or the total solution.